So the moral of the story, if the sequence converges, then every subsequence converges to the same limit. All right? Maybe I'll just write that again for the folks back home. If AN converges, every subsequence converges to the same limit. This is definitely a fact to know. Actually, this fact is often even more useful in the contrapositive. I hope you remember what the contrapositive means. If you have an if-then, if it's like if P then Q, the contrapositive of that is if not Q, then not P. It's the negate. You negate each one and turns the order around. And something you learned in discrete math, I hope, is that the contrapositive is equivalent to the original statement. So this means, another way of saying this is, if every subsequence does not converge to the same limit, then AN does not converge. I'm going to write that down. So this is the contrapositive, which is also true. This is logically equivalent to what I said before. And I'm going to change the if-then around, the other way around, but negate each side. It will say, if some subsequences do not converge or converge to different limits, that's the negation of the second part. Then the negation of the first part, AN diverges. All right? And this actually is pretty much the best way of showing that a sequence diverges. This is something we haven't done a lot of. We did a bunch of examples showing that this or that sequence converges. But to show something diverges is kind of a pain to do directly using definitions. But using this is fairly easy to show that something diverges. So I'll just say use this to prove that some sequence diverges. And let's try an example. How about, we did this example using the definitions, but you'll see this is easier to do using this little theorem here. So AN equals minus 1 to the power n. That is minus 1 plus 1 minus 1 plus 1, etc. All right. Now, using the definitions, this is not so hard. If you think about it in terms of neighborhoods, I think you will agree there is no specific point that all of these numbers get close to in its neighborhood, right? Because some of them are close to 1, some of them are close to minus 1. But they're not all close to any point in particular. That's why it diverges. But you can easily demonstrate it using this theorem here, written in the contrapositive. It says if some subsequences do not converge or converge to different limits, then the original sequence diverges. So I'm going to do it this way. I'll say we'll show it diverges by finding two subsequences with different limits. Two subsequences having different limits. If it converges, all the subsequences have to have the same limit. So if you can find two subsequences having different limits, then it must not converge. And it's not so difficult to find two subsequences having two different limits. Anybody think you can find two subsequences which have two different limits? Yeah. Yeah, so one would be this. Just take all the minus ones. And one would be this. Take all the plus ones. These are both subsequences. Do they converge? Yes. This one converges to minus 1. This one converges to plus 1. Since they converge to different limits, so these subsequences have different limits, So that means AN diverges. That's how we do it. This should be sort of your go-to method in general to show something diverges. If I ask you to show something diverges, this is probably the way you want to do it. Easier than using the definitions. Than trying to negate the epsilon thing is usually harder than that. All right. Any questions about this so far? Subsequences. If the sequence converges, all subsequences also converge to the same limit. That's the first of the two big facts. I said I had two big facts for us to talk about today. And I said one was simple and the other is not so simple. This was the simple one. I don't know if that seems simple. But if you think about it in terms of the neighborhoods, it's obvious that the subsequences must go to the same limit. All right? That was the simple one. The other one is less simple. It's not super complicated, but it's not really something you might think of on your own. I mean, probably you would if you thought for long enough. But the other one concerns when is it possible to find subsequences which converge. Like in this example here, I just picked out two subsequences that converge. And it was pretty easy in that example. I tried to design the example to make you think of those two subsequences. I would like to know, when is it possible? When is it possible to find convergent subsequences? Even if the sequence diverges, you can find convergent subsequences. Is it always possible to find a convergent subsequence? Actually, it is not always possible, so I'm going to say not always. Why not? Here's an example. This is a simple example. 1, 2, 3, 4, 5, etc. This has no convergent subsequence. Do you believe me? These things go up to infinity, and any subsequence would also go up to infinity. No subsequence of this converges. They all go up to infinity. So this has no convergent subsequence. I will say, sort of parenthetically, since the sequence itself sort of goes to infinity. If you mind, we haven't really said technically what I mean by that. I mean it's unbounded. But any subsequence then must also be unbounded, and therefore none of the subsequences converge. But it turns out this is the only obstruction. So if the sequence is bounded, then it is automatically possible to find a convergent subsequence. And this is my second big fact of the day. This is such a big fact, actually, it has a name. This is called, I'll write it as a theorem. It's called the Bolzano-Weierstrauss theorem. Bolzano-Weierstrauss theorem. One of the big theorems in real analysis. This also appears in the official course description for this class, right along with the monotone convergence theorem, which we talked about last time. The Bolzano-Weierstrauss theorem. It says if the sequence is bounded, if AN is bounded, then it has a converging subsequence. Then it has a convergent subsequence. If the sequence is bounded, then it has a convergent subsequence. This is the Bolzano-Weierstrauss theorem. It is important, and by the end of class today, I hope you are all thoroughly convinced that this must be true. If AN is bounded, it has a convergent subsequence. I would encourage you, actually, later on today, if you like, go on YouTube and search for Bolzano-Weierstrauss. If you just type Bolzano-Weierstrauss, it will try to complete the phrase for you. And the first choice will be Bolzano-Weierstrauss theorem, because that's what it is. The second choice will be Bolzano-Weierstrauss wrap. And if you click that link, you will find somebody wrapping a proof of the Bolzano-Weierstrauss theorem. This is about as awesome as you think it is, which is to say, kind of. And that someone happens to be our very own Fairfield University professor, Steve Sawin. I don't know if you know him, but his office is right over there. This has got like 50,000 views on YouTube. This is as viral as people like Steve can expect to achieve. People like Steve includes people like me also. So I'm not trying to defame Steve. His rap skills. Let me just say, his rap skills are adequate. His backup rappers are woefully inadequate, I would say. But that's part of the charm of this video. So you should check it out. Actually, the proof that I want to talk about is basically the same as what Steve says in the rap. So if you don't like the way I say it, maybe check it out. There's actually someone has made sort of another version using Steve's vocal track with like diagrams illustrating the proof at the same time. It's actually pretty well done. So check that out too. Anyway, if AN is bounded, then it has a convergent subsequence. Just first of all, I'm just going to try and draw like a vague picture here. If it's bounded, that means that the whole sequence is stuck between m and minus m, right? That's what it means for a sequence to be bounded. So all the terms of the sequence have to be like this, right? And I'm drawing them in no particular order. We are not assuming that it's monotone or anything like that. If it's monotone, then the whole thing converges, right? By the monotone convergence theorem, it says if it's bounded and monotone, then the whole sequence converges. This does not say that it converges. It just says that it has a convergent subsequence. The idea behind this is basically because if I just continue to draw points here, of course there are infinitely many points in that sequence. These infinitely many points, you should feel like they're going to have to pile up somewhere, right? Now, they could actually pile up in more than one place, but somewhere there's going to be a pile up of something. And if you choose, remember, a converging subsequence means you only have to choose some of them. If they're all piling up somewhere, then you should be able to choose only some of them so that they actually approach a specific limit. Even though it is possible to have two different subsequences which converge to two different things, like we've seen before. So, I turned the page again. You know they hate it when I do that. Remember the very simple example we did just a moment ago was +1 and then -1, right? This one, the terms look like this. They just keep on going back and forth. Can you find a subsequence which converges? Yeah, you can. We just, you can find more than one, right? You could choose a subsequence which always stays on the right side, and then that one converges. Or you could always stay on the left side, and that one converges. All right? This is always possible as long as the sequence is bounded. It's the very basic idea is because there's going to be infinitely many points in there, there's got to be some of them that pile up somewhere. They can't be infinitely, evenly distributed across the whole thing. That's not possible. Yeah?
Can you find infinitely many subsequences to converge? Like if you were to say, skip some of the ones and skip some of the negative ones, stay on the right.
Yeah.
Infinitely many?
Yes. Yeah, that will always be possible. Like in the +1, -1 example, you could take, say, 3 +1s and then the rest -1s. Or you could take 4 +1s and then the rest -1s. They all converge to -1. Yeah, that's a great observation. Okay, let's see if we can talk a little more formally about the proof of this, the Bolzano-Weierstrass theorem. Although I'm going to skip a few steps, I just want to give you the basic idea. Steve's proof is actually slightly more detailed than I'm going to say, although he says it pretty fast. It's still kind of hard to understand. It's good to have the diagrams along with it. I have a hard enough time understanding, I hope you don't mind me saying, I have a hard enough time understanding a lot of the real rappers, and they're not like trying to talk about math proofs. Steve, he talks kind of fast, but he says basically the same stuff that I'm going to say. So here's the idea. I'll just write, we're going to do the idea. Although I'm going to say almost everything that is necessary. The idea is I'm going to think of this in terms of a bunch of intervals. So I'm going to say come on now. I'm going to call I1 to be the whole closed interval from minus m to m, right? That's sort of where we begin. And all the terms of the sequence are in there, right? Now, since there's infinitely many terms in this sequence, I'm going to consider what happens if I cut it in half. Say divide the interval in half at 0. That's where the middle will be. I'm going to say at least one of these two halves, minus m to 0 and 0 to m, at least one of those includes infinitely many points of the sequence. Maybe both of them do. But because there are infinitely many terms in the sequence overall, you divide the thing in half, still it must be true that one of those sides at least has infinitely many things in it. Now it's possible they both have infinitely many things in it, that's fine too. All right? At least one of minus m0 and 0m includes infinitely many points of the sequence. So I'm going to choose I2 to be one of the sides which has infinitely many. And if they both do, it doesn't matter. You can choose either one. So choose I2 to be 1/2, which includes infinitely many. Points of the sequence. All right? Now, on my picture, it's not clear which side has infinitely many, but if let's say we imagine that these points really start to cluster around here. Maybe they actually have a limit or something, all right? Then, in my example, this whole thing, I'll write this in red maybe. This whole thing would be I1, but I2 would be just this side, right? Because it's the side which contains infinitely many things. And then you continue this procedure. You divide the interval in half every time. And it always must be true that there are infinitely many points on one or the other half, right? Because there's always infinitely many points in the interval to begin with. In this case, I3 would be this side because it's the one which contains infinitely many points of the sequence. So I'm going to also choose I3 to be half of I2, again, which includes infinitely many points of the sequence. Anybody see where I'm going with this? Can you think of what I'm going to say next? Perhaps something from our past. You keep on doing this, right? I choose I1, I2, I3. Each one is half of the previous one. The half chosen so that it has infinitely many of the terms in it. This seem familiar, reminiscent of something in our past? Yeah? What do you think? Yes, when you have closed intervals all inside of one another, what's that thing called? Yeah, the nested intervals property. Remember that? The NIP. Well, what happened on my screen? What happened to? Oh, I think. Yeah, okay. So now, because of the nested intervals property, there must be one point at least which is in all of those, right? So I'm going to say, let me just say continue like so. Then these are all closed intervals. They are nested because each one is just a half of the previous one, so they will automatically be nested. So then by the nested intervals property, there exists some point x that is in I(n) for all n, all right? So on the picture, it would look something like, in this case, I4 would be, I4 would look like that half. I5, I guess, would be this half. I6 would be half of that. I'm not sure actually which half based on the picture there, but you can keep on zooming in and in and in. Would you believe me if I said that point x is the limit of a subsequence, right? It might not be, there may be more than one place where infinitely many points sort of accumulate. So that point x might not be the limit of the entire sequence, but it definitely will be the limit of some subsequence. And how could you choose some subsequence which approaches x? You can just choose any point that you like in each one of these intervals. Take any point of I1, then take any point of I2, then take any point of I3. Those points, if you just choose individual points, they must converge to x, which is the point at the middle. All right. The details of that are something that I don't think we need to explain in detail. Steve does explain in detail. If you watch the wrap, you will see. So there exists x in IN for all n, and we can choose points. Choose points a and 1 in I1, a and 2 in I2, etc. You know, in general, just choose some point a and k in IK. We are picking individual points in each of those increasingly small intervals, and then this part you need to do some epsilons if you really want to do the real proof. Then I will just say it. A and k converges to x. So there is a convergent subsequence.
And this is even if the original sequence diverges?
Yes, that's right. The only thing is it has to be bounded. Yeah. All right. This is the point when Steve says, "Are you down with that?" And the backup singers say, "We're down with that." That's sort of the chorus. You'll see. It's worth watching once in your life. He actually does a fairly good job of explaining it in a way that is memorable, I think, which is good. All right. I think we got 8 minutes left. I think is enough time to do a comprehensive exam problem concerning the Bolzano-Weierstrass theorem. Unless there were questions about the statement. All right. Let's see if we can do. This was I looked this up in my old comps. This was 2020 comp question number 24. All right. Actually, I didn't look up how many people did this question. To me, this seems like an easy one, but I don't know. Maybe they all seem easy. So part A just says, state the Bolzano-Weierstrauss theorem. All right, I don't think we need to do that. It says if a sequence is bounded, then it has a convergent subsequence. All right. So, but it's worth you guys knowing. You will be expected to know these things, you know, by name. There are not other names for this theorem, really. Everybody calls it the Bolzano-Weierstrass theorem. Okay, the next part says define. They just want you to give the definition of xn converges to some limit L. So for this one, second one doesn't have anything to do with the Bolzano-Weierstrass. They just want you to write the epsilon definition of convergence, which I think also we don't really need to do right now. Part C is a little more interesting. It says, give an example of, and then you got 3 little parts. This is something on the comp, they often have little parts inside of parts. A bounded sequence, AN, that diverges. You want to give me an example? This you're just supposed to make something up. A bounded sequence that diverges. Yeah. Sine n. Yeah, that's an awesome example. So I thought somebody was going to say -1 to the n, which is the one we just talked about. That is a bounded sequence which diverges. Or I like this one better. Sine of n. It is bounded because the sign of anything is always between -1 and 1, but it doesn't converge. That's because if you just plug very high values for n into sine of n, it doesn't like approach any specific value. You know, everybody knows that's how the sine function works. Excellent. Okay, and then number 2. Give an example of, it says two subsequences of an that converge. So they want you to take your answer from part 1 there and find two subsequences which converge. Actually, this is very, very hard to do for sine n. So let's just forget she said that. It was a good answer for part 1, but if you were really doing this on the test, you would have gone back and changed your answer from part 1 because it's hard to do for part 2. Anyway, for -1 to the n, that is easy. Actually, we did that. This is the same thing we talked about already. So two subsequences which converge would be like that and also like that, right? Do you believe me that that's very hard for sine of n? Does anybody happen to know a subsequence of sine of n which converges? The answer is no, you don't. But maybe I'll try to make you agree with me that. See, this is sine of x, right? Sine of x, the values itself, if you just consider x values, the y values don't approach any limit. But we are considering only the integers. So sine of 0 is 0. Anyone tell me what is sine of 1? The answer is no, I cannot tell you what is sine of 1. It's just some weird number. Like there's no, that's not a thing. I mean, it is a thing, but it's not a thing anybody knows about, right? You put it into your calculator. Sine of 1, well, this is pi over 2, which is like around 1.5, right? So sine of 1 is around here somewhere. I don't know what that is. Sine of 2 is here. Sine of 3 is, that's pi, so sine of 3 must be slightly to the left of that. But anyway, these numbers, there's no real formula for what those values are. They're just, all of them are crazy, irrational numbers, don't really have any specific meaning to them. And that's why it's hard, and maybe it should feel like maybe it isn't even possible, but because of the Bolzano-Weierstrass theorem, it must be possible to find a sequence of those particular values which do actually converge to something. That's very weird, but it is weird but true. Anyway, two subsequences of A and converge. That's that. So I'm going to just cross this one out. I love that example for part 1, but I would never want to try and answer that for part 2, so I'm going to forget about it. And then part 3, give an example of an unbounded sequence. What's your favorite unbounded sequence? That's all it says, just any unbounded sequence. What do you think? 1, 2, 3? Yeah. Everybody should have given that as the answer. I mean, didn't have there. Of course, other answers you could give. Okay, and then part D, which is really the interesting part, in my opinion. It says define Cn as a sequence to be n times sine of n pi over 2. And it says show that Cn is unbounded but has a convergent subsequence. So you're actually not really using the Bolzano-Weierstrass theorem in any of these parts. They're all just trying to get at the same kinds of ideas, though, about subsequences and boundedness and unboundedness. Now, this one is much easier to handle than the one that she suggested earlier, which was just sine of n. Why is this so much better, sine of n times pi over 2? Because those are values actually that you do know something about. If we just examine like what do the values of sine n times pi over 2 look like? The first one would be sine of pi over 2, and then sine of 2 pi over 2, which is just pi, and then sine of 3 pi over 2, and then sine of 4 pi over 2, which is 2 pi. What are these values? Ordinarily in this class, I don't care about sines and cosines of anything, but just for the sake of this right now. Anyone remember what is sine of pi over 2?
1, 0, minus 1, 2.
Yeah, this is 1, this is 0, this is minus 1, that's 0 again. And then the next one will be 1 again. And these values will repeat. 1, then 0, then minus 1, then 0, then 1, and so on. They will cycle like that through 4 different values, all right? Does that help? I don't know. Shows Cn is unbounded but has a convergent subsequence. Well, first of all, can we find a convergent subsequence? Yeah.
Just the zeros.
Yeah, just the zeros. So this, remember, is not the sequence that we are talking about. We're talking about n times that, all right? So our sequence is not really the same. Our sequence is n times that stuff. But because there are zeros in there, those are still going to be zeros after you multiply by n. And so that will still work as a subsequence. So a converging subsequence is simply 0, 0, 0, right? And that is obtained by taking the, I suppose, the even numbered terms from the original sequence. So in fact, if you really wanted to dazzle the judges, you could say C2n. Actually, C2n equals that, right? If I use only the even numbered terms, I get 0 every time. Awesome. Okay, so that shows, oh, it's time to go. Why is it bounded? No, it is unbounded. Why is that? Can I just say in a moment? N times sine of n pi over n. Anybody feel like that's unbounded? You can see a convergent subsequence if you look at what happens to the zeros. What about if you look at what happens to the ones? What happens to the ones? Yeah. Yeah, if you look actually just at the plus ones, they get multiplied by n every time. So if we look at this sequence, in fact, it's something like C sub 4k plus 4n plus 1. I'm looking at the first one, the fifth one, it's this one, the next one. The ones that say ones in those positions, they're always one more than a multiple of 4. This sequence is well, it's equal to 4k plus 1. And then if the k goes is big enough, then this is unbounded. It's a simple idea. It's hard to write out the details, but if I look at these positions, they all look like 1 from the sine part, but then you multiply them by n, it becomes unbounded because the n itself is unbounded. All right, that'll do it. Sorry I went over a few minutes. Sorry to the people at home. I messed up at the beginning. See you tomorrow.